Okay, let's talk about data management. So first of all, I want to point out, as we go, we're going to learn more and more functions, and it's going to be hard to keep track of everything that you have learned. So if you go to this website, you'll find a nice cheat sheet with all of the main functions that you'll probably need to know throughout this course and beyond. All right, that being said, our objectives today are to talk about numerical functions, and then character functions and apply functions. So first I want to present some motivating data that we'll use especially when we talk about character functions and apply functions. So here I have some students' names. Here I have hypothetical math scores, science scores, English scores. And I'm going to create a data frame that has the students in the first column, math scores, science scores, English scores. And I'm going to put strings as factors equals false in this data frame. When I call this data frame, because I'm going to want to do some parsing later on for their names. So here's what the data set looks like. All right. That being said, let's move on to numerical functions. And I can't stress enough, I would go to that reference card and keep that handy. But so the main mathematical functions that you may come across, algebra type functions, are these: absolute values, square root, ceiling, floor, trunc means truncate, round, significant digits, cosine, sine, tangent, log. You'll have to read the help files to use each one of them if you want to know how to use it appropriately. The main statistical functions, the basic ones, are the mean, median, standard deviation. MAD stands for mean absolute deviation. Quantile, range, sum, min, max, and scale gets us z-scores. So probability functions, I'm going to spend some time on these because I think it's a good review. We'll talk about quantile functions, probability functions, or what we know as cumulative distribution functions, random number and density, random number generation and density functions. The common ones are, here you have d norm, r norm, q norm, p norm. So d norm computes the density for a normal distribution. R norm generates random variables from a normal distribution. Q norm is a quantile function for a normal distribution, and p norm is the probability function for a normal distribution. Excuse me. You'll notice d binom, r binom, p binom. These are the same things, but for a binomial distribution. So here, d binom computes the probability mass for a binomial random variable. R binom generates binomial random variables. Probability that x is less than or equal to x, or the CDF, the binomial distribution, and the quantile function for a binomial distribution. So what value of x puts a specified probability to the left. If you're not familiar with quantiles, you might want to brush up on quantiles. Those I've found to be tricky in the past. You might guess what these are: F distribution, T distribution, uniform distribution, and there are many, many other distributions. You should see the URL for more. All right, so the first thing you'll want to use is this args function. That just is going to go pull up the arguments that you can specify for a function. So for example, if I run args of pt, pt says I need a t value, or that's my quantile, and pt, so I'm going to have to input a quantile value for a t distribution and the degrees of freedom. You may or may not know what a non-centrality parameter is. Probably not if you've only had one stat class, but we'll just assume that it's 0, so don't worry about that. More specifically, read the help file, and it'll say density distribution function, quantile function, and random generation for the t distribution. So density distribution function for p, quantile, and random number generation is r. So it tells you the inputs here. You could have inputs X, Q, P, and N, and so on. R binom. Here, if I wanted to generate binomial random variables, N tells me how many I'm going to generate. The size, that's the actual, so that's N in the notation. So if I have a binomial distribution with N is equal to 10 and probability equal to P, size would be 10, probability would be equal to P, and N would tell me how many of those guys I want to generate. And dnorm, you can see what those arguments are. The default is mean 0, standard deviation 1 for standard normal distribution, and again, read the help file of that. And you'll notice the help files are basically all the same. The only difference is it tells you what distribution you're dealing with. Okay, and it'll give you some examples. So again, now that we're starting to learn more and more functions, you're going to have to learn a lot by doing and less by listening. So I'm going to go through a lot of these pretty quick. So I'm just going to change my significant digits to 2 here. And R unif stands for random uniform distribution. So this generates 10 realizations or random variables from a standard uniform distribution or uniform distribution with endpoints 0 and 1. You'll notice if I run it again, I get completely different numbers. If I run it again, I'll get completely different numbers, and so on. So here I've changed my significant digits to 2, so if I have 2 zeros, I have to round, I have to report 2 significant digits, so that's why sometimes there's a different number of decimals. Now we've talked a little bit about this set seed function. What set seed function will do is allow you to replicate the data that you've generated. So these aren't exactly purely random variables. They depend on a seed. That's a complicated issue, so I just want to illustrate what it does. So here I've set the seed, generated these uniform random variables. If I set the seed again, it will be exactly the same. So that's why in computational statistics, these are sometimes called pseudo-random numbers. They're not totally random. I can reproduce them. Okay, so I'm just going to make some curves to help us understand quantile functions, distribution functions, and CDFs. You can read more about this curve. Read it carefully, but expression, this is going to be a function of x, and a curve will draw a curve for it. And you can change a lot of the arguments, like make labels and titles and line types, just like you would in a plot function. But the main thing is, here we'll tell you the function that you want to draw a curve of, and then from and to, that will give you your x-axis. So what I want to do is draw a curve of the uniform density function, so density of the uniform distribution. And you have to use argument x when you're using the curve so that it knows that it's a function of x. If this were a different letter, it would get confused. So here, I'm going to plot the uniform density function. I'm going to specify my x limits. You can also just specify them -1.1 and then 1.1. Specify it just like you would in a plot function. So everything else is the same as arguments for a plot function. And here it drew my uniform distribution, which has density 1 between values 0 and 1, and has density 0 otherwise. What's P? I'm going to run curve of P unif. That's the CDF for a uniform distribution. I'm going to change some plotting colors and symbols to make it a little bit legible. You could make this prettier on your own time if you want. I'm going to add a legend. It says D unif for density. D unif is what I used for the CDF. So for a uniform distribution, what's the probability of being less than 0.4? The answer is 0.4. So the red line represents that. The black line represents the density. So for example, if I wanted to just do what's the probability of a uniform random variable being less than or equal to 0.7, the answer is 0.7. The area to the left of 0.7 and under this curve is 0.7. What's d-unif? This is the simplest density function we have. It just takes on value 1 if we're between 0 and 1 and 0 otherwise. So you'll also notice what's the probability of a uniform random variable being less than negative 0.2? It's 0. And the CDF tells us that too. What's the density of a uniform distribution outside of 0 or 1? It's 0. So the density of a uniform distribution at 1.2 is 0. So a little less standard, we might be interested in the t-distribution. So dt says I'm going to draw a curve for the density of a t-distribution. The main argument you have to input is the degrees of freedom. All right, so let's draw that. Here I just drew student's t-distribution with t degrees of freedom using the curve function. And qt, what's this going to do? This gives me a value of t, so it's a quantile function. So this means the area to the left of negative 2.2 on this t distribution is 0.025. So that's what the quantile means. So the probability that t is less than or equal to negative 2.2 is equal to 0.025. So quantiles are always a little bit trickier in my experience. So let's look at the probability that I'm to the left of 2.2, 0.026, a little bit of rounding error. So this isn't exactly negative 2.2. Remember, I'm rounding the significant digits. Okay, now I'm going to actually draw what the quantiles are on the axis. So remember the axis function on the bottom. That's what the 1 tells me. I want to make these symbols twice the size. And I'm going to draw where I'm going to draw the ticks are at quantile function, or at the quantiles, 0.025 and 0.975. When I have a t-distribution and degrees of freedom 10. And then labels, let's run this, and I can explain better what it does. So at told me where to draw, labels tells me what to draw. So this expression is handy. You can read the help file for expression. But t bracket 0.025 says go draw this t and index 0.025. That's what the bracket does. You have to use the expression. So that can be kind of a neat trick. If you want to do Greek symbols, for example, you can type expression of theta and it will draw the Greek symbol theta. All right. So here's my t density function. This value here has 0.025 to the left. This value here has 0.975 to the left. I'm going to illustrate this by actually generating. What's RT going to do? It's going to generate, if I type t.data, it generated 1,000 realizations from students' t-distribution with 10 degrees of freedom. Here they all are. I'm going to make a histogram of these, a very basic histogram. Probability equals true rescales this so that these boxes represent probabilities instead of counts on the y-axis. And I'm going to draw a curve, the same curve, over the top. So here I actually have data and a corresponding scaled histogram. And here I drew the density over the top. And you can see we might want to clean it up, make the y-axis a little taller if I wanted to redo this. So here's my t density theoretically. Here's my data generated from a t distribution. And what's the area to the left of 2.28? It's 0.97. 0.97. So these did very different things. Mean, this counted the proportion of my generated data that were less than 2.28. In theory, because 2.28 is the 97th percentile, 97% of the observations, if I generate data from the t-distribution, should be less than 2.28. This tells me theoretically what should happen. So this is the probability that t is less than 2.28. It's 0.97. This is the proportion of times that that actually happened when I generated data from that distribution. Okay. Again, if this is a lot, please go back and review your probability distributions from your intro stat class. One more plot, and we have categorical data or categorical distributions like binomial distribution. What have I done here? I've plotted p-binom. So what's this do? Let's first show you what this is getting. P-binom of 0 through 20. So this, if I have a binomial distribution with parameter n equals 20 and p is equal to 0.5, this is the probability that x is less than or equal to 0. This is the probability that x is less than or equal to 1. This is the probability that x is less than or equal to 2, and so on up through the probability that x is less than or equal to 20. Okay. So I'm just plotting these probabilities, and a nifty trick is in plot, one option is type equals s here, which says plot a step function. So the CDF for a binomial distribution is actually a step function because probability that x, for example, is less than or equal to 10 is here, which is about 0.25, but the probability that x is less than or equal to well, let me start over. The probability that x is less than 10 is here. The probability that s is less than or equal to 10 jumps up to here. Right? So we actually have a step function. Alright, and then this is, I'm just going to go through this real quickly for fun. If I wanted to generate multivariate normal data, if you read the help file for MVRNorm, so multivariate data can be trickier to generate, but in the mass package, MVRNorm is a simple way to do it. The help file says I want to generate multivariate norm. N is the number of variates to generate, mu is the mean, sigma is a variance covariance matrix. So I have to specify the variance of each variable and all of the covariances. So here's how you would use it. I need to specify a mean. So here's the mean. I have 3 variables, each with mean 0. The first variable has variance 1, second variable has variance 1, third variable has variance 1. This 0.8 represents the covariance between the first variable and the second variable. The covariance between the first variable and the third variable is negative 0.5. You'll notice this matrix has to be symmetric because the covariance between the first and third variable better be the same as the covariance between the third and the first variable. So here's my mean covariance. Notice one's positive, another covariance is negative, and another is 0. So here I'm going to generate my data, and if you actually type mvn.data, you'll notice I've generated 10,000 vectors now. So if I have multivariate data, I have to have 3 realizations for each time I generate a multivariate vector. So if you want to do plot, it's not going to look very nice. It's only going to plot the distribution of, or the data for the first 2 variables. So you might want to change that to a data frame when you're plotting later on. So here's my first variable, second variable. Here's the scatter plot with the second variable on the x-axis and the first variable on the y-axis. Recall sigma. The covariance is 0.8, so the covariance here is 0.8. What if I want to look at the the covariance between x1 and x3, that's up here. Notice it's negative 0.5, and so on. Alright, so we're getting a little bit fancier on generating data. And this is really just a fun plot. You can fast forward if you want. What I'm going to do is just illustrate the beauty of randomization. So I'm just making a blank plotting window, and what I'm going to do is generate some multivariate normal data, but I'm going to allow some of the parameters for how I plot and generate the data to be random. So for example, my color, I'm going to take a random sample of the numbers 1 through 50, and the sample size is going to be 4. So for example, color is 20, 13, 33, and 23. That's my plotting colors. Mu, I'm going to generate my mean. In this case, the mean of my data is going to be 0.41, 0.9 for my bivariate data. I'm going to generate a correlation. You can read more about the R beta function. I'm going to generate, or then I'm going to record the covariance matrix. So in this case, here's my covariance matrix. Here's my mean vector. So I'm going to generate data from that multivariate normal distribution. How many am I going to generate? Some random number. I'm going to generate, in this case, 1,018 realizations. So here's my actual generated data. And here, you'll notice CEX, that's the size of my plotting character, is going to be random. Color was randomly determined earlier. X limit, I'm going to fix that to be negative 5 to 5, and my Y limit also. Okay. So here, the options for plot are random, the number of realizations are random, and the size of the plotting character are random. So now I'm just going to rerun all of this code again. And you'll see the size now is smaller, the colors are different. And I can rerun this code over and over again to show you a visual depiction of the idea of randomness. How would you reproduce that exact same plot? You should have ran set.c. So, character functions. So, character functions are functions that are designed to be applied to characters or texts, so such as like names and things like that. The main functions are in-character, char, or for in-character, substring, grep, sub, string split, paste, all of these things. Again, read the help files for all of these to get more comfortable with them. But string split and paste are the most common, so you can do most everything with string split and paste. So let me just show you an example of how you would use character functions string split. So here I have this character that just says, I am Josh Haviger. And how would you use string split? The first thing you're going to want to do is read the help file. You have to input a character vector. Split tells you how you're going to split. So what is it looking for when it splits this guy into different objects? So carefully read the help file or run this code. What's string split? It's going to input, I'm going to input X and look for spaces, and whenever I find a space, I'm going to split that guy up. So now I've created a list with 4 elements. The elements are defined I am Josh Haviger because there was a space between I and M, so it's split. Space between M and J, so it's split, and so on. And now I could create What is this doing? Let's split the string, run this code just as I did before, get the first element of the list, and then the third element within the first element. And that is my first name indeed. Do the same thing, but for the last element, my last name. So I took this character vector and created an object called first that's just the character of my first name. So really good for parsing, or if you're doing big data type management stuff, you'll need to know how to do this kind of thing. All right. What did I do with paste? Paste puts strings back together. So I pasted the objects first and last and created one single object with Josh Haviger. So that's the basic idea with character functions. Again, string split and paste are pretty much all I've used in my career, but there are, I'm sure, dozens of functions that may or may not work more efficiently for you. So it's a matter of taste. So just to help you understand, string split doesn't have to look for spaces. So remember, here's my string. I told it to split by the letters IG. So what did it do? It's just going to search all of the letters, and then it found the IG. And so it deleted those and made everything to the left of this and everything to the right of it its own element in this new string. All right, apply functions. If you read, so apply functions, the main, application of this is I like to apply functions across rows or columns. For example, means or sums or medians can be applied to each column of data. So a lot of functions automatically do this, but other ones won't. You can also see the function by, which operates similarly to apply, and other functions in the help file for apply. Or also see that URL with the note card for the main apply type functions. So the pseudocode for the apply function, and this works for many of the similar apply functions like lapply, sapply, listapply, etc., is like this. So you first have to input what you're applying a function to. So here's the data input. Margin is usually 1 or 2 for rows or columns. And I never remember off the top of my head, so I just try both until I get the one I want. And then you input a function. So the function can be a function that you'll define. We'll talk more about that later. Or it could be a built-in function like mean or median, etc. So for example, let's do this. So apply roster -1 to mean. What did that do? Let's remember what roster data is. So here's the roster data. This is a data frame with 1, 2, 3, 4 columns. I don't really want to apply the mean function to these names. That doesn't make any sense, and we'll kick back an error. But what I might want to do is look at the mean math score, the mean science score, and the mean English score. So this function said, here's the data I want to consider. Not the first column, but I do want to consider the second, third, and fourth columns. I want to apply across columns 2. So if you inputted a 1, it would do rows. And the function I want to apply to this data is the mean function. So for example, you can guess what will happen if I do this. That took the mean of each row, so the mean of 502, 95, and 25, which is 207. So that's not what I want. I probably want the mean math score, mean science score, mean English score. So second argument is rows or columns. You can actually pass options that the function you want to apply will take. So for remember, above. one optional argument for the mean function is this guy trim. So you can't say mean and then have parentheses mean and to do a trim mean, but what you can do is run code like this, and so this or other option, that option will be passed through the mean function when you apply the mean function. So you'll notice now the trimmed mean was computed, the trimmed mean was computed, the trimmed mean was computed to each column, or columns 2, 3, and 4. So just an illustration of what we might do for this to create a new data set. So what did sums do? It got the sums for each row, so it added these, and these, and I might want to stack each sum for some other statistic next to my data. So sums, I'm going to say the sum total score for John Davis was 622. So that's how I might create a new data set containing sums. And of course you can use different things besides sums. Alright, so finally let's get to revisiting our example. Here's our roster. And remember our goals are to combine scores to get a single score for each student, assign a letter grade using a bell curve, and then we want to sort alphabetically. So number 1, combine scores to get a single score for each student. First thing we'll notice is how are we going to combine scores when we have things like math scores and science scores are not on the same scale. So a 502 in math can't very easily be compared to a 95 in science. So that's where the scale function comes in handy. So what did the scale do? It took my math scores and returned a z-score. So you'll notice if you do this, math minus mean, so it takes each individual math score, subtracts off the mean, and divides by the standard deviation. If you do that, you'll get 0.013 for the first math score, 1.143 for the second, and so on. So that's all scale does. Fairly simple function. It just does that for us. The advantage of using scale is here I can get standardized z-scores for an entire data frame. So it will apply the scale, so scale can be applied to each column one at a time. Okay, so I'm going to create a new data set. Save my score. So I'm going to get my scores, excuse me, to skip down a line, get my scores, and get a mean score. And save that as score. So what did this do? I have my standardized scores, 0.013, 1.078, 0.587 for student 1, right? If I average those, I get 0.56. I get 0.92 for the second student, 0.86 for the third student. So this is a natural way for me to come up with a single score that represents how a student performed. So now I've gotten z-scores for each of these entries. So 502 has a z-score. I got that z-score. 95 has a z-score for science. And 25 there's a z-score for English. So on average, the average z-score was 0.56. So that means the student did better than the average on average. The student did below average. The student did 1.16 standard deviations below the mean on average. All right, now number 2, I want to assign a letter grade using a bell curve. So first I'm going to create quantiles for my score, 0.8, 0.6, 0.4, 0.2. So let's see what that did. It says the 80th percentile for a z-score was 0.74. The 60th percentile for a z-score of 0.44 was a 60th percentile. The z-score of negative 0.36 was a 40th percentile. Okay, so that's what the quantiles do. And now I want to do something like this. If a student was greater than the 80th percentile, I'm going to give them an A. So this person was greater than the 80th percentile. Recall the 80th percentile was 0.74. They got a 0.92, so they get an A. And you can guess what these are going to do. I'm going to assign a grade of B if a person is between the 80th and the 60th percentile. A C between the 60th and 40th, and so on. Okay, so here are my scores. I found quantiles for them, so you'll notice this person scored a 0.56, which was between the 80th and the 60th percentile, so they got a B. This person, like we said, scored above the 80th percentile, so they got an A. This person scored between the 40th and 20th percentile, so they got a D, and so on. All right, one last objective. I want to sort alphabetically, so we're going to have to apply some character functions. So first I'm going to create this guy name. I'm going to run string split, so read the help file. So I'm going to go get the students' names and split my string whenever I see a space. So I have two names, right? So the first student's name was John Davis, so now I have John and Davis, and he is the first element of my list. Second element of my list is a vector containing values Angela and Williams, and so on. A neat weird trick that I was not too familiar with until recently is this function. This guy here, that's actually a function. You can read the help file for that. Help. And it'll tell you that it's a way to extract elements. So for example, if I run this guy on 5 and 10, this is the function I'm applying. I'm applying it to this vector 5 and 10, and I'm saying go get the first element. If I do this, look at the vector 5, 10. This function says go get the second element. Okay, so if I do this, S applies, so I'm going to apply this function, which extracts the second element from the vector name. Okay, so that got all of their last names. First name, extract the first element. So I'm going to create roster. I'm going to create a new roster that has first name and last name separated. And I'll remove the original first column. It has their full name. So that now looks like this, so that I can alphabetize. And I will let you guess how we could sort these guys according to name.